Good morning and welcome to this fifth module of Theory of Machines. Before we go into the present module, let us briefly review what we have seen in the previous module. In the previous module, we have seen the classification scheme of kinematic pairs. We saw that kinematic pairs can be classified based on degree of freedom, or based on type of contact, or based on type of closure. Having said that, let us go into the learning outcomes of the present module. In the present module, we are going to see what is meant by a kinematic chain or a kinematic linkage, and in specific we are going to see what is an open linkage, what is a closed linkage, and then we'll define what we mean by a mechanism, and then we'll define what is a machine. These topics were perhaps introduced by a famous person whose photograph is shown over here. His name is Franz Roulox. In fact, he is the person who for the first time defined or classified kinematic pairs into lower pair and higher pair. He has developed very systematic and simple notation for representing kinematics of machines, and thus he is called father of kinematics. You may want to see further details about this father of kinematics at this Wikipedia website shown over here. Having said that, let us go and look into the first topic, that is kinematic chain or kinematic linkage. A kinematic linkage is formed when a number of kinematic links are connected one after the other through kinematic pairs. This kind of concept can be clearly understood when you look at an animation. Let us look at it over here. You have one link connecting to another link, then second link connected to third link, then third link is connected to fourth link. So these four formed a kind of a sequence of kinematic links connected by kinematic pairs. So depending on the number of links, you may have certain degree of freedom of this kinematic link. The topic of degree of freedom will differ to a later module. Let me just show once again. This is link 1. Link 1 is connected to link 2. Link 2 is connected to link 3. Link 3 is connected to link 4. So all these four put together, they form a kinematic chain, or we call it a kinematic linkage. Okay, for reasons that will be clear to you in a while, we call it an open kinematic linkage or open kinematic chain. Let us see another kind of silly example. This, you may not have any application of this, but just for the sake of illustration, I'm trying to show another animation over here. Okay, again here you have four links of different shapes. You may not find these. I'm just picked up a hypothetical case. You can see that one is picked and connected here, then another one is connected by a kinematic pair, another one is connected by a kinematic pair. So all these four are joined successively. Link 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. So this is again another example of a kinematic linkage or kinematic chain. Again, the reason why we are calling open, it will be clear perhaps in the next couple of slides. Okay, as can be seen in the previous case, all the joints forming or connecting the kinematic links, this is a revolute pair. Again, between link 2 and 3 is a revolute pair. Again, between 3 and 4 is a revolute pair. That is not the case in this kinematic chain. This kinematic chain, you have a rectangle, a square block going into a slot. So this is a sliding pair. You have a pin going into a hole here. That is a revolute pair. You have again a pin going into a hole here. That is a revolute pair. So when we say a kinematic chain, it is successive connections between links by forming kinematic pairs. That pair could be a turning pair, revolute pair, or in general any kinematic pair. Okay, so let us briefly see what we mean by kinematic chain. A kinematic chain is formed when a number of kinematic links are connected one after the other through kinematic pairs. The first two examples we have seen, they are open kinematic linkages or open kinematic chains. Let us try to see an example of a closed linkage. In a closed linkage, see what is happening. This whole yellow thing is one link. You may consider it to be a tabletop fitted with a pin over here and a hole over here. And you can see that this red link is pushed all the way down so that it's always in touch with this tabletop, and then another green link is forming a kinematic pair over here, and then you have another kinematic pair over here, and see what's happening. This fourth link is connecting back to the first link. So first link is connected to the second link is connected to the third link is connected to the fourth, and fourth is connected back to the first link. If such a thing happens, we call it a closed kinematic linkage. And often while we are representing kinematic linkages this way, the size of the link really doesn't matter. Let me try to explain what I mean by it. You have a big link here. You can see, you can consider it to be a tabletop. Okay, to the tabletop you are joining link 2. This tabletop is link 1. You have this as link 2, and link 3 is connecting to link 2. Then link 4 is connecting to link 3. And now see what's happening. The link 4 is connecting back to the link 1, which is the table. And obviously when we are concerned with the motion, the size of the link often does not matter. Okay, what I'm going to show here is, I'll cut a portion of it. There's no change in the relative motion. Okay, now one half will be cut. Okay, there is no change in the relative motion here. Another piece is cut. No change in the relative motion. This is a 4-bar mechanism. Why we call it is, there is one yellow link, a red link, a green link, and a blue link, and all of them are forming a closed shape. That is the reason why you call it a closed link, kinematic linkage, or closed kinematic chain. And often this is called a 4-bar linkage with revolute pairs. Each joint here or joint here or joint here or joint here, they are all revolute kinematic pairs. Let us look at another example of a closed linkage, or closed kinematic linkage, or closed kinematic chain. You have a brown link here into which you are dropping a slider. We kind of assume that this slider can only slide along it. Somehow or the other it is constrained. Okay. On the top of the slider you have a pin into which this link 3 is getting connected, to which another link is connected, and this is connected back to link 1. So link 1 is connecting to link 2, link 2 is connecting to link 3 is connecting back to link 4 is connected back to link 1. Okay, again I'm kind of trying to show that size really doesn't matter. You can cut it short. Let me try to animate it from the beginning. Okay, you have link 1, link 2, link 3, and link 4. Link 2 is connected to link 1. Link 3 is connected to link 2. Link 4 is connected to link 3. And now link 1 and 4 are connected. So 1, 2, 2, 3, 3, 4, 4, 1. So it's forming a closed kinematic chain or closed linkage. Because you have a slider, you can see that this blue link, it can only slide along. Because it can only slide along, it is called a slider. Whereas this pink link, it can rotate, make one complete revolution. It is called a crank. So it is slider, crank, kinematic linkage or kinematic chain. Having seen that, we will look at one more example. We'll try to complicate the issue just a little bit. You have two blue links here. Okay, let me try to animate it. You have two blue links and see what they can do. This blue link can slide This blue link can slide. You have slots in which these two can slide. Okay, and then you have another link connected. Okay, you can see that it can move. Motion is possible. I would strongly encourage you to number the links. Number this as link 1, link 2, link 3 and link 4. You'll again see the same pattern. Link 1 is connected to link 2, link 2 is connected to link 3 is connected to link 4 is connected to back to link 1. Okay. Having said all that, we note one important thing. In all the earlier animations we have seen, all the links in those examples, they are either moving in a single plane or they are moving in planes parallel to each other. Okay, and that is the reason why we call all these linkages as planar linkages. When we say planar linkage, we mean that all the links move either in a single plane or planes parallel to each other. So what we have seen is planar kinematic linkages or planar kinematic chains. Once we have a chain, we can define what we mean by a mechanism. When we say a mechanism, what we really mean is mechanism is a kinematic linkage in which one of the links is fixed. When one link in a closed linkage is held fixed, the linkage is termed as a mechanism. Once we know what is a mechanism, we kind of try to extend that into a machine. When the links in a mechanism are properly designed to take the loads arising out of movements, we term that mechanism as a machine. In specific, the line demarcating between mechanism and machine, in one way you can think it's a fine line. Basically what we mean is when we use the term machine, we indicate that forces are also transmitted. When we say mechanism, what we really mean is we are trying to track down the displacements or movements, not displacements, movements of various links, how it is transformed. For example, we call a door closing mechanism. Like the automatic door closing, we call it a mechanism because the forces involved there are very smaller. Whereas in other case, if you have big gates covering the compound walls, you need to have a big motor and links that move the door. In such case, we call it a machine. So the same entity, depending on the nature of forces, magnitude of forces, the magnitude is very high, we term it machine. Whereas if the forces are very small, we can neglect them, and what we are interested in is only movements, we may call it a mechanism. Okay, that's all we have for today. We'll try to quickly summarize and close this module. What we have seen today is a kinematic linkage. A kinematic linkage is a successive connections between links. That could be an open kinematic linkage, a closed kinematic linkage. A closed kinematic linkage, you have the last link connects back to the first link. Some kind of a loop is formed. Similarly, what all we have seen so far is planar kinematic linkages. We'll concentrate for most part on planar kinematic linkages. Okay, and we saw that in kinematic linkage, if one link is fixed, we term that linkage as a mechanism. If the links of the mechanism are designed to take up the loads involved, we term the mechanism as machine. We kind of closed the loop here. We started with what we mean by machine, what we mean by theory. We defined theory of machines, and then a machine, and then we defined a kinematic link, and then a kinematic pair, and then a kinematic linkage, and then a mechanism, and came back to machine. In some sense, we finished kind of one topic which can be closely knit. With that said, the module is complete. Thank you very much for staying with us. If you have any questions or comments or suggestions, please email them to theoryofmachinesselftaught@gmail.com. Thank you once again. Have a good day.